Section A, factoring.
Factors are two numbers that when multiplied together give you another number. Like 2 and 3 are factors of 6 because 2 times 3 equals 6. And 4 and 5 are factors of 20 because when you multiply them together they equal 20. 2 and 10 would also be factors of 20. So would 1 and 20.
Now sometimes we're given a particular number and asked to list the factors of that number. So we're going to go through an example and show you how that works. Take a look.
If we're going to factor the number 36, we can start with the 1 because it's a factor of every number except 0. We know that 1 times 36 equals 36, so 36 will be the second factor we list right here. Now the process becomes kind of hit or miss, so let's go in a logical order and try the number 2. 2 is a factor of 36 because it divides evenly into 36. So what number do we multiply 2 by to get 36? The answer is 18. That means 18 is another factor, and we put it right here.
See how we're working towards the middle? Next, is 3 a factor? Well, 3 multiplied by 12 equals 36, so 3 and 12 are both factors. 4 times 9 equals 36, so they are both factors. 5 doesn't make the grade because we can't multiply it by any whole number to equal 36. 6 multiplied by 6 equals 36. So we list it as a factor one time, right here. We don't need to write it twice because all we're doing by putting it in this list is saying that it's a factor.
Since 6 times itself equals 36, we know we're done with our factoring because there's no whole number between 6 and 6. Lining it up this way, we can see all the factors of 36. 1, 2, 3, 4, 6, 9, 12, 18, and 36, laid out in sequential order. Let's try one more of these, using the number 18.
As always, we start with 1, and we see that 1 times 18 equals 18. So these are both factors. Is 2 a factor? Well, 2 times 9 equals 18, so both of these are factors. How about 3? 3 is also a factor because 3 times 6 equals 18. 4 isn't a factor, and neither is 5, because we can't multiply them by any other whole numbers to get 18. Now we know we've found all possible factors because we've already used 6, and there are no whole numbers between 3 and 6 that work.
These numbers we just factored are examples of something called composite numbers. That means they have more than 2 factors. For example, the number 20 is composite because it has 6 factors: 1, 2, 4, 5, 10, and 20. But don't get caught thinking all numbers have many factors. There's another kind of number that actually has only 2 factors total. These numbers are called prime numbers.
A prime number is a number that only has 2 factors, 1 and itself. For example, 7 is a prime number because it only has 2 factors, 1 and 7. No other 2 positive integers can be multiplied together to give us the number 7. Same thing with 13. The only 2 positive integers we can multiply to equal 13 are 1 and 13. 5, 17, and 19 are also prime numbers.
Now, take note that the number 1 is a special case because it's neither prime nor composite. 1 only has 1 factor, which is itself. So the only factor of 1 is 1, and by definition, a prime number must have 2 factors, 1 and itself.
So the difference between prime and composite numbers is that prime numbers have only 2 factors, and composite numbers have more than 2 factors. Got that? Now there are times when you'll need to know which numbers are prime and which are composite.
Back in the 3rd century BC, there lived a man of invention named Eratosthenes. They called him the second Plato. They even nicknamed him Beta because it means second. Eratosthenes calculated the Earth's circumference by paying attention to the Earth's shadows and using simple geometry. Modern-day accounts show he calculated the circumference of the Earth accurately to within 1%. He was also a librarian and invented a way to pinpoint all prime numbers. This guy was smart.
Eratosthenes created a sieve, like this one. Except with his, we can figure out all the prime numbers less than a certain designated number. The sieve is like a filtering system that eliminates all of the numbers that aren't prime and leaves us with the ones we want. Let's use the sieve to figure out all prime numbers less than 100.
Our first step is to figure out all of the prime numbers less than the square root of 100. If you don't know about square roots yet, don't worry too much about it right now. We're going to look at that more in the next section. For now, just know that the square root of 100 equals 10.
So what are all the prime numbers under 10? We've got 2, 3, 5, and 7. Remember, we know this because each of these numbers has only two factors, 1 and itself.
Next, we need to write out all of the numbers from 1 to 100 like this. Now we figure out all of the multiples of 2, 3, 5, and 7 that are less than 100 and cross them off. For example, the multiples of 7 are 14, 21, 28, 35, 42, 49, 56, 63, 70, 77, 84, 91, and 98. So we got to cross them all out. We do the same thing for the multiples of 2, 3, and 5, and we get a sieve that looks like this. All of the remaining numbers that are not crossed off are the prime numbers less than 100. So, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97 are the primes less than 100. And that's how the sieve of Eratosthenes works.
Remember, too, that the sieve works with any whole number you want. So if we wanted to find all the prime numbers under 225, we'd just choose that as our starting number and follow the same steps.
It's important to know what the prime numbers are, especially the first 5 or 6, because we're going to be using them throughout our next section for factoring. And you'll most likely be using them throughout your math courses. So you might want to do the sieve a couple of times to really get them down.
Sure, it'd be easier if we just told you, but you need the math practice.
All right, let's take a look at the next section. We're going to be delving into the wild and woody world of arboriculture. That's the study of trees. Why don't you jot that down for your SATs?
Section B, tree diagrams and prime factorization.
We're about to use tree diagrams to get smart about prime numbers. Tree diagrams help us break big composite numbers down into the product of smaller prime numbers with exponents.
We call them tree diagrams because they sort of look like little trees with branches, except they have numbers on them. We start at the top of the tree with a big composite number and work our way down the branches, getting smaller and smaller until we have merely twigs with prime numbers. Check it out.
Say we've got the composite number 72, and we factor it down to 12 and 6. We can't go home yet because these numbers are also composite, and we got to factor until we've got all prime numbers. So, 12 will factor into 4 times 3, and 6 factors into 2 times 3. Then our 4 factors down even further into 2 times 2. So now we've got 2 times 2 times 3 times 2 times 3. Notice we're now at the point where we have all prime numbers. The next step is to express those numbers exponentially. In other words, to write them as base numbers with exponents. Since we have 3 2's, that gives us 2 to the third power, or 2 cubed. And we have 2 3's, so we have 3 squared. That means the prime factorization of 72 equals 2 cubed times 3 squared.
Now, how do we know to start with 12 and 6 in that last example? Well, we could have started with 8 and 9, which are also 2 factors of 72, and gotten the same answer. It's not important which 2 factors of 72 we start with, only that we get started. Once we complete the factor tree, if we did it right, we'll get the same prime factorization either way.
So our goal is to get big composite numbers factored down into a product of prime numbers with exponents. Let's give it another go. Check out the tree diagram for the number 81.
If we factor 81 using the tree diagram, we start with the factors 9 times 9. Notice these aren't prime numbers, so we've got to keep going. Since 9 can be factored into 3 times 3, we get 3 times 3 times 3 times 3, or 3 to the 4th power. If we multiply it out, we see that 3 to the 4th power equals 81, which means we factored correctly, because 81 is our original number.
Now let's try a big scary number like 336. With a big scary number like this, if it's an even number, the easiest thing to do is just keep dividing by 2 until we can't anymore.
Dividing by 2, we see that 2 goes into 336 168 times. So, our first two branches are 2 and 168. Now, we can break 168 into 2 times 84. 2 goes into 84 42 times, so these are on our next branches. 42 can be broken into 2 times 21. Now, notice that 2 doesn't divide into 21 evenly, but we can still break 21 down into smaller numbers. We know that 7 times 3 equals 21, so we factor it by breaking it down to 7 times 3. Neither 7 nor 3 can be broken down any further because they're both prime numbers. That's good. It's what we want. But we're not done just yet. You see all those 2's? We can't forget about them. They're still part of our prime factorization, so we gotta include all 4 of them in our answer. When we do, the ultimate prime factorization of 336 is 2 to the 4th power times 3 times 7. If we want to check our work, we can multiply this out to get 2 times 2 times 2 times 2 times 3 times 7 equals 336. Since our numbers equal 336, we know we did it correctly. Now, our big scary 336 isn't really that big or that scary.
With the prime factorization of a composite number, you've got to get all the way down to the nitty-gritty of it. You're only finished once you've got all prime numbers and you've given them the right exponents.
Okay, now that we know how to find all the factors of a composite number and how to find prime numbers, let's step it up a notch.
Section C, the greatest common factor.
The best way to introduce the greatest common factor is to pick a couple numbers and factor them like we've been doing. The greatest common factor is going to be the factor with the highest value, or largest quantity, that appears in both lists of factors. Let's try this with the numbers 15 and 20.
Our first step is to factor both our numbers. We're going to do the listing method this time, so let's list the factors of 15 and 20. The factors of 15 are 1, 3, 5, and 15. And the factors of 20 are 1, 2, 4, 5, 10, and 20. The next step in finding the greatest common factor is to figure out all the factors that these two numbers have in common. In this case, we notice that 1 and 5 are in both lists, so they're called common factors. Now remember, the greatest common factor is the one out of these two that has the highest value. In this case, the greatest common factor is 5 because it's a common factor of 15 and 20, and it's greater than the other common factor, 1.
Another thing to know about the GCF is that it's possible the GCF of two numbers will equal 1.
For example, with the numbers 7 and 15, 1 is the greatest common factor because after we factor them out, we see that 7 and 15 have no other factors in common. So, 1 is both their only common factor and their greatest common factor.
Since we found the GCF in our previous examples by listing factors, now we're going to try another way. Remember way back about 3 minutes ago? We used the tree diagrams to do prime factorization. Well, we're going to use that same prime factorization stuff to help us find the GCF another way. Let's take a look.
Say we're searching for the GCF of 12, 28, and 48. First, we're going to factor them down to prime numbers using the tree diagram, and then put them into numbers with exponents. So, starting with 12, 12 breaks down to 6 times 2, which further breaks into 3 times 2 times 2, or 3 times 2 squared. 28 equals 14 times 2, which breaks into 7 times 2 times 2, or 7 times 2 squared. And 48 equals 12 times 4, which breaks into 4 times 3 times 2 times 2, which equals 2 times 2 times 3 times 2 times 2, or 2 to the 4th power times 3. Now let's figure out the GCF.
After we get the prime factorization, we've got to look at the numbers and their exponents and figure out which will be a part of the GCF. Any prime factor we choose for our GCF must be a factor of all 3 of the original numbers because that's what makes it a common factor. So, when we look at the prime factors, we see that 2 is the only one that's a factor of all 3 numbers. So it's going to be the lone base number in our answer. The only thing left is to figure out what exponent 2 will have.
When deciding on the exponent, we look at the exponents for each of the 2's. We've got 2, 2, and 4. To get the GCF, we just take the smallest exponent. So in this case, we would use 2 as our exponent. That means our GCF is 2 squared.
So our GCF, 2 squared, equals 4 when we multiply it out. 4 is the greatest common factor of 12, 28, and 48 when we express the GCF in whole numbers.
A great way to check our work is to list the factors like we did in the first method and see if we got the same answer. See how when we list out the factors in whole numbers, 4 is the GCF. That means we did our factoring correctly.
So, when we're looking for the GCF, first we want to get the prime factorization of our numbers. Then figure out which prime numbers are factors of all our original numbers, and how many times each of those prime numbers is represented. Then, we take the smallest exponent, and we've got our GCF. Now we're going to take a look at something that's kind of like the cousin of the GCF, but with its own identity.
Section D, the least common multiple.
Before we get into the least common multiple, or LCM, let's take a minute and talk about what a plain old multiple is. A plain old multiple is what you get when you multiply one number by another number.
All right, let's take the number 3. What are its multiples? Well, 1 times 3 equals 3. 2 times 3 equals 6. 3 times 3 equals 9. 4 times 3 equals 12. 5 times 3 equals 15. 6 times 3 equals 18. 7 times 3 equals 21. And 8 times 3 equals 24. So the first 8 multiples of 3 are 3, 6, 9, 12, 15, 18, 21, and 24.
And now, it's the artist formerly known as the least common multiple. Give it up for the LCM. To find him, just look in a few lists of multiples. He's the number with the smallest numerical value that appears in all your lists. Take a look.
These are some multiples of the numbers 6, 10, and 15. What we want to do is figure out the least common multiple of all 3. So, the LCM is the multiple that 6, 10, and 15 all have in common and has the smallest numerical value. You might notice that 60 is a multiple in all 3 lists, but so is 30. Because we're smart, we know that 30 is smaller than 60, and 30 is the smallest multiple they all have in common, which means 30 is the LCM of 6, 10, and 15.
When you're listing multiples, the fastest way to find the least common multiple is to look at the multiples of the largest of the numbers. So, for our previous example, to find the LCM of 6, 10, and 15, 15 is the largest number, so you would look to the multiples of 15. First, try 1 times 15, or 15. 15 is not a multiple of 6 and 10, so next try 2 times 15, or 30. 30 is a multiple of both 6 and 10, as well as 15, so our number is 30.
Listing multiples, like we just did, is one way of finding the least common multiple, but there is another way to do it. Any guesses?
Look in the back of the book.
Nice. But no. We're going to use the prime factorization method. Let's use the same numbers, 6, 10, and 15. Now remember way back about 2 minutes ago when we found the GCF? Well, our first step here is the same. We're going to factor with tree diagrams and then give our prime numbers exponents.
So, if we take 6, we get the prime factors 2 times 3. 10 breaks down to 5 times 2, and 15 gets mapped out so that its prime factorization is 5 times 3.
Now we've got all our prime factors and we need to express them with exponents. This part is a little different from the greatest common factor. To represent the LCM with prime numbers and exponents, we need to take every prime number that appears as a prime factor and write it once with the biggest exponent that appears. Take a look.
Since the prime numbers we see are 2, 3, and 5, we're going to use each of these one time and give them an exponent. For the LCM, we use the biggest exponent for each prime number that is represented. This is different from the GCF, where we use the smallest. Notice in this example, the most each prime number appears in a single factorization is 1 time. So the biggest exponent we can use for each is 1. That means the LCM of 6, 10, and 15 is 2 to the first power times 3 to the first power times 5 to the first power, or 2 times 3 times 5. See how when we multiply 2 times 3 times 5, it equals 30, which is what we got before when we compared multiples with whole numbers.
Excuse me.
Dude, get the mustard, dude!
When you multiply your prime numbers with exponents, they equal my whole number. I checked it out.
What now, dude?
There's nothing left now but math. Hey, let's get the LCM of 10 and 25.
Doing the prime factorization of 10 and 25, 10 breaks down to 2 times 5, and 25 breaks down into 5 times 5, or 5 squared. At this point, we're already down to our prime numbers, so we want to represent all the prime numbers that appear. In this case, we've got 2 and 5. So what is the most number of times 2 appears in a single factoring? Well, it's just one time. That means our exponent for 2 is 1. What about 5? The most 5 appears in a single factoring is 2 times, so 2 is our exponent for 5. That means the LCM of 10 and 25 is 2 times 5 squared. If we multiply the LCM out, we get 2 times 5, which equals 50. And remember, we can check the LCM by listing the multiples out this way. And here we see that 50 checks out as the LCM.
Ta-da! So that's how we find the LCM. We do the prime factorization of our numbers, then represent all prime numbers with their highest exponents. Now fancy this. It's already time for a review of this section. So sit back and absorb.
Factors are two numbers that, when multiplied together, give you another number. A composite number has more than 2 factors, while a prime number has only 2 factors, 1 and itself. When we look for the prime factorization of numbers, we can use tree diagrams to break a composite number down into the product of smaller prime numbers. If we're looking for the GCF of a set of numbers, we do the prime factorization for each of the numbers. Then notice which prime numbers appear as factors of all numbers. We take those prime numbers and represent them with their smallest exponents. This gives us the greatest common factor between our factored numbers. If we're looking for the LCM for a set of numbers, we need to represent every prime number, and we need to represent it with the biggest exponent it has in one factorization. This will give us the least common multiple in our set of numbers.